If we left Earth in 2026 and aimed for the nearest star, how long would the trip really take? The question sounds simple, but the moment you compare our fastest spacecraft to the actual distance, everything you think you know about space travel starts to break. Because leaving Earth is one thing, crossing the gap between stars is something else entirely. The nearest star to the Sun is Proxima Centauri, and it is about 4.25 light-years away. That is roughly 40.2 trillion kilometres, or about 25 trillion miles. Those numbers are so large that they stop feeling real, so it helps to convert them into something more familiar. The average distance between Earth and the Sun is 1 astronomical unit. To reach Proxima Centauri, you would have to cover about 268,770 of those Earth-Sun distances in a row. So when people hear nearest star, their brain shrinks the gap before the facts even show up. In normal life, nearest means close enough to matter. In space, nearest can still mean almost incomprehensibly far. And that changes the whole question right away. Because if the nearest star is still this far, then this is not about taking current space travel and stretching it a little bit. This is a completely different scale of problem. Then there is the next fact that makes it worse. Light itself needs time to get there. Light is the fastest thing in the universe. Nothing we can build with mass can move that fast. Light travels so quickly across the solar system that people often think of it as instant. Sunlight reaches Earth in around 8 minutes. A radio signal to the moon takes a little over a second. That sounds fast because for most human situations, it is fast. But for the nearest star, even light starts looking slow. A signal moving at the speed of light needs about 4.25 years to reach Proxima Centauri one way. That means if a spacecraft somehow got there and sent a message home immediately, Earth would still wait more than 4 years just to receive that message. There would be no live conversation, no real-time control, no immediate celebration back on Earth. The nearest star is so far away that even information takes years to cross the gap. That is important because it means the problem is not only propulsion, it is also communication, autonomy, timing, and patience. A star mission cannot work like a Mars mission or a Moon mission. At those distances, the speed of light itself becomes a limit you feel in the mission design. So if even light needs years, then maybe the solar system must be tiny compared with the journey, right? That sounds reasonable, but that intuition is also wrong. Most people picture the solar system as the Sun, the planets, some asteroids, maybe Pluto, and then empty space, but the actual frontier of the Sun extends much farther out. NASA describes the Oort cloud as a vast outer region that may stretch perhaps 1/4 to halfway from the Sun to the next star. Its outer edge could be somewhere between 10,000 and 100,000 astronomical units. That is a huge written range, but the message is clear either way. The outer solar system is not a neat boundary near the planets. The Sun's distant domain fades outward across a massive part of the space between stars. That means the phrase leaving the solar system is more complicated than people think. You can leave the region dominated by the solar wind and still be nowhere near the true outer frontier of the Sun's wider gravitational environment. The journey to another star does not begin after a short exit from home territory. In a broad sense, home territory already reaches deep into the Gulf, and that makes the next milestone sound very different. Voyager 1 entered interstellar space in 2012. That was historic. It crossed the heliopause at about 122 astronomical units from the Sun, roughly 18 billion kilometers, or about 11 billion miles. That is one of the greatest achievements in the history of robotic exploration. It proved that a human-made object could move beyond the bubble formed by the solar wind and into the local interstellar medium. But once you compare that to Proxima Centauri, the scale becomes brutal. Proxima is about 268,770 astronomical units away. Voyager 1 entered interstellar space at about 122 astronomical units, so the first human-made object to enter interstellar space had only covered a tiny fraction of the total distance to the nearest star. It had not come close to finishing the job, it had barely started it. That distinction matters because people often hear interstellar space. and think it means the stars. It does not. Interstellar space is not the same thing as another star system. Crossing the heliopause is a major scientific milestone, but it is not the same as practical interstellar travel. Voyager 1 did something historic, but it also exposed how much farther the real journey still is. Then the question gets sharper. If our most famous deep space probe could enter interstellar space and still be almost nowhere relative to the nearest star, then the real issue is not whether we can launch something off Earth. We already can. We have done that many times. The real issue is speed across extreme distance. And that forces a harder way of looking at the whole subject. The challenge is not, can humanity leave Earth in 2026? That part is easy. The challenge is what kind of technology, energy and timescale would be needed to cross a gap so large that even light spends more than 4 years on the trip. Once you frame it that way, the whole story changes. This stops being a question about rockets leaving a planet and becomes a question about whether our civilization can handle distances that make normal travel language almost useless. That is why the word nearest is misleading from the start. It suggests a destination just beyond our reach. But Proxima Centauri is not just beyond our reach in the normal sense. It sits at a distance that breaks the way people naturally think about motion, delay, and exploration. The nearest star is not nearby. It is simply the least far star in a universe where even the smallest gaps between suns are enormous. And that is only the first layer of the problem. Because once you accept the scale, the next surprise is that you are not even aiming at one simple target. You're aiming at a whole nearby stellar neighbourhood, and that makes the destination more complicated than the distance. The next problem is the target itself. People say the nearest star like it is one clear point. It is not. The nearest star is Proxima Centauri, but Proxima is part of the larger Alpha Centauri system. So if you say you are going to the nearest star, you are not talking about one isolated object sitting alone in space. You are talking about a nearby stellar neighbourhood with multiple stars, different environments, and different mission targets. Alpha Centauri A and Alpha Centauri B orbit each other once about every 80 years. Proxima is much farther out, and it takes more than 500,000 years to orbit that inner pair. That means the closest star to us is actually part of a complicated 3-star family. That matters because the destination stops being simple the second you define it properly. You're not just choosing a distance, you're choosing between different stars in the same system, and those choices change the science, the risk, and the value of the mission. Then the next question gets uncomfortable. If the system has multiple stars, why does everyone focus on Proxima? The answer is distance. Proxima Centauri is closer, at about 4.25 light years. Alpha Centauri A and B are slightly farther away, around 4.3 to 4.35 light years. On paper, that difference looks tiny. It sounds like almost nothing. But when your mission time is measured in decades, centuries, or longer, even a small fraction matters. At interstellar scale, a little bit closer is still a real advantage. But closer is not the same as better. That is where the target starts getting harder to understand. If your only rule is to reach the first possible star as fast as you can, Proxima wins. It is the closest first. That makes it the obvious headline target. But if your real goal is to study planets, search for possible habitability, or one day think about long-term exploration, then the nearest option may not be the best option. And that tension sits right at the centre of the whole story. The shortest trip and the smartest trip may not be the same mission. So then the next question becomes the obvious one. What is actually there? This is where the system becomes more than a set of stars. NASA's current reporting says there are 3 confirmed planets orbiting Proxima Centauri. Worlds around Alpha, Centauri A and B are much harder to confirm, which means the best defined planets in the nearest stellar neighbourhood are around Proxima, not around the brighter stars. That immediately gives Proxima a huge advantage for science. It is not just the closest star, it is the closest star with confirmed planets we can talk about seriously, and the most important of those planets is Proxima B. Proxima B is the showpiece because it is roughly Earth mass, and it sits in the kind of position that gets attention very quickly. It has a year that lasts about 11.2 Earth days, and it orbits at about 0.0485 astronomical units from its star. That distance is extremely small compared with Earth's orbit around the Sun. Earth sits 1 astronomical unit from the Sun. Proxima B is far, far closer to its star than Mercury is to ours. So the first real exoplanet target in the nearest stellar system is not some distant outer world. It is a close-in planet packed tightly around a dim star, and that changes the emotional feel of the destination right away. It stops being an abstract star name and becomes a real planetary target with actual numbers, actual orbit data, and actual mission relevance. You are no longer just saying go to Proxima Centauri. You are saying go to a system where there is a roughly Earth-mass planet orbiting very close to a red dwarf and finishing a year in just over 11 days. Then the next question matters even more. Does that sound anything like Earth? Not really. Proxima B is estimated at about 1.055 Earth masses, so in terms of mass it sounds familiar enough to pull people in, but the environment is not familiar. It sits extremely close to a dim red dwarf star because red dwarfs are much fainter than the Sun. For a planet to get enough starlight in that kind of system, it has to orbit much closer in. That means the first truly reachable exoplanet on paper is not an Earth twin around a Sun twin. It is a planet in a compact, intense system built on very different rules. That difference is important because people often hear Earth mass and quietly turn it into Earth-like. Those are not the same thing. Similar mass does not mean similar climate. Similar size does not mean similar atmosphere. Similar orbital energy does not mean similar safety. Proxima B may be one of the most important planets ever discovered because it is nearby and roughly Earth mass, but that does not make it a second Earth waiting for us across the void. And once you say that clearly, the target starts feeling stranger, not simpler. Its year is 11.2 days, its orbit is about 0.0485 astronomical units. It circles a red dwarf, not a sun-like star. That means the first exoplanet we can realistically discuss as an interstellar destination already forces you out of the comfortable template most people carry in their heads. If you were hoping the nearest star system would give us a clean copy of home, it does not. It gives us a much harsher lesson. The first reachable planet is reachable only in the sense that it exists nearby on the map. Its actual conditions may be far less welcoming than the word Earth mass suggests. So then the next question becomes even more dangerous. What if the closest target is also the worst target? That is where Alpha Centauri A and B come back into the story. Alpha Centauri A is a sun-like star. Alpha Centauri B is a slightly cooler K-type star. Those are, in some ways, more comfortable stars for people to think about when they think about long-term habitability. They are more familiar classes of stars. They are not identical to the Sun, but they are much closer to the kind of stellar environment that makes intuitive sense to us. Proxima, by contrast, is the active red dwarf in the family. That one detail changes a lot. Because once the target is not just nearest, but nearest confirmed planetary system, you also have to ask what kind of star is driving the system. And in this case, the nearest star may also be the most hostile option in the neighbourhood. That means the obvious destination starts to unravel the moment you stop looking only at the distance column. This is where the whole mission concept gets more serious. If Proxima is the closest target with confirmed planets, then it becomes the natural first choice for a probe. But if Alpha Centauri A or B turn out to offer more stable, less hostile environments, then the slightly farther stars may be more scientifically attractive in the long run. So the clean answer disappears. The closest destination may be the best for arrival time, the best for current exoplanet certainty, and still not be the best place if you care about safer long-term planetary environments. And that is the real shift in this section. The target is no longer a simple answer. It is a trade-off. Proxima gives you the shortest distance. Proxima gives you confirmed planets. Proxima gives you Proxima B, a real world with a real orbital data and real scientific value. But Proxima also gives you a red dwarf environment, and that pushes the whole conversation into a much less comfortable direction. Meanwhile, Alpha, Centauri A and B are slightly farther away, but they may represent more attractive stellar environments if confirmed planets around them ever become clear. So even before you launch, the destination is already arguing with you. The nearest star is not one object. The nearest system is not one answer. And the planet that looks like the best first target may turn out to be the hardest one to trust. And that raises the tension again, because now the problem is no longer just the distance. The problem is that after all that distance, you may still be heading toward the wrong place. Getting off Earth is not the hard part. That sounds wrong at first because launches look violent, expensive and dangerous. But for a mission to another star, launch is only the first filter. The real problem starts after that. There are 3 different things people mix together. The first is leaving Earth's surface. The second is leaving Earth orbit. The third is leaving the solar system with enough speed for the trip to matter. Those are not the same challenge. Humanity already knows how to do the first 2. We have launched people, probes, landers, telescopes, rovers, and heavy cargo. We know how to get off the ground. We know how to get into orbit. We know how to send spacecraft outward. But that third step is where the whole question changes. Because once you stop asking, can we launch, and start asking, can we leave the sun with serious speed, now you're in a different fight. Now you're dealing with orbital mechanics, energy, trajectory design, and speeds that has to stay useful after the spacecraft is no longer being pushed. That is where interstellar travel stops being a launch problem and turns into a physics problem. And that difference is exactly why people underestimate it. A rocket leaving Earth looks fast because by normal human standards it is fast. But fast for launch and fast for a star are not even close to the same thing. The numbers prove it immediately. New Horizons is a perfect example. At launch, it reached about 58,536 kilometers per hour, or 36,400 miles per hour relative to Earth. That is the highest launch velocity ever achieved by a human-made object relative to Earth. By any normal standard, that is extreme. It is fast enough to cross entire countries in minutes. It is fast enough to make most space missions look slow. It sounds like the kind of number that should put a star within reach. It does not. That is the point. The fastest launch ever is still nowhere near fast enough for a practical mission to the nearest star. This is where the language starts breaking down again, because people hear fastest ever launched and assume that must place us somewhere near the edge of what is needed. But when the destination is 4.25 light years away, that kind of speed is still deep inside the category of far too slow. Then the next question becomes obvious. If the launch is already that fast, why is it still not enough? Because launch is only the opening move. After that, the spacecraft still has to deal with the shape of the solar system, the sun's gravity, and the route it takes outward. That is why gravity assists matter so much. New Horizons did not just blast straight to Pluto on launch energy alone, it used Jupiter for a gravity assist, and that boosted its speed by about 14,000 kilometers per hour, or 9,000 miles per hour. That shaved about 3 years off the trip to Pluto. 3 years is not a small correction. That is mission changing. It shows that once you start talking about deep space, the launch vehicle is only part of the story. The trajectory matters just as much. That is one of the most important lessons in all of spaceflight. Your engine gets you started. Your path decides whether the mission is merely possible or actually efficient. And that lesson gets even more important when people talk casually about leaving Earth in 2026. Because that phrase makes it sound like the date is the main issue. As if the question is mostly about when we choose to go. It is not. A spacecraft launched in 2026 with normal deep space architecture is still trapped by the same laws as one launched before or after. It still has to escape Earth. It still has to build enough heliocentric speed to move outward fast. It still has to deal with mass fraction, which is the amount of the vehicle that has to be propellant versus payload. It still has to work within real power limits. It still has to use gravity assists if it wants extra speed without absurd fuel cost. and it still runs straight into the travel times measured in decades, centuries, or far worse. So yes, a launch year changes history. It changes who builds the mission, which technology is available, what the budget looks like, and what the public remembers. But it does not change the underlying physics. The sun does not care what year you picked. The distance does not care what year you picked. Orbital mechanics do not care what year you picked. That is why the phrase, "if we left Earth in 2026, can be misleading if you do not define what kind of mission you mean. If you mean a mission built from the same broad family of deep space methods we already use, then 2026 does not unlock Starflight. It just starts the clock on another very long outbound journey. And this is where the interstellar problem really begins. Not on the launch pad, not at liftoff, not when the boosters separate. It begins after the dramatic part that people usually think of as the mission. Once you leave Earth, you still have to beat the sun. That means gaining enough outward speed that the spacecraft is not just escaping, but escaping fast enough for the timeline to matter. Then you still have to cross the huge empty gulf beyond the planets. Then you still have to deal with communication delay, because the farther the spacecraft goes, the less real-time control means anything. Then you still have to deal with arrival, which is its own problem, because reaching another star system at high speed is not the same as slowing down and studying it well. That is the brutal structure of the challenge. Getting off Earth is the easy part. Staying fast is harder. Crossing interstellar distance is harder. Talking to the spacecraft across years of delay is harder. Arriving in a useful way is harder. And that is why the middle of this story has to get more serious. Because the real puzzle is not launching a mission. The real puzzle is building a mission that can get somewhere before the civilization that launched it has changed beyond recognition. That is the scale of the problem. Not just speed, but meaningful speed. Not just escape, but escape that matters. Not just leaving home, but leaving home fast enough that the destination is still part of the same human story. And when you put it that way, the next step gets much harsher. Because once you compare the actual speeds of our best machines to the distance of the nearest star, you find out that even our legends are still crawling. The next reality check is speed. Not theoretical speed, not future speed. Actual speed from the fastest machines humanity has ever built. Start with Voyager 1, because it sounds like the strongest case we have. Voyager 1 is the farthest human-made object ever built. As of August 21st, 2024, NASA listed it at 164.7 astronomical units from Earth, moving at 17.0 kilometers per second, or about 38,026.79 miles per hour, relative to the Sun. That is an extraordinary achievement. It is one of the greatest engineering successes in history. It has outlived governments, presidents, entire generations of technology, and still keeps going. But this is also the first serious reality check, because even Voyager 1 is nowhere near Starflight speed. That matters because Voyager feels fast in a way that is emotionally convincing. It is distant. It is historic. It is outside the familiar solar system in the way most people picture it. It is the kind of mission people point to when they want proof that humanity can reach the stars if it just keeps pushing. But when you stop reacting to the legend and look at the numbers, the mood changes very fast. Voyager 1 is not showing us that we are close. Voyager 1 is showing us how far away close really is. Then the next fact makes that even harder to ignore. Voyager 1 launched in 1977. That means it has been travelling for nearly half a century. And in all that time, it still has not covered even 1,000th of a light year. That is the kind of number that breaks people's internal sense of progress. Nearly 50 years sounds enormous on a human timescale. Whole careers fit inside that. Entire technological eras fit inside that. And yet in interstellar terms, that span is still tiny. NASA describes the Voyagers as escaping at more than 3 astronomical units per year. And for Voyager 1, the figure is about 3.5 astronomical units per year. That is impressive for a deep space probe. But it is also the proof that deep space is not the same thing as interstellar travel. This is the key difference people keep missing. Voyager 1 is not failing. It is doing exactly what it was built to do. The problem is that the nearest star is so far away that even a mission this successful barely changes the scale of the challenge. A spacecraft can be one of the greatest achievements in engineering history and still be moving far too slowly for a star mission to make sense. Then you need a second benchmark because maybe Voyager sounds old. Maybe the you think fine, that was 1970s technology. What about something faster? That is where New Horizons comes in. New Horizons had the highest launch velocity relative to Earth ever achieved by a human-made object, about 58,536 kilometers per hour or 36,400 miles per hour. That is a huge number by any normal standard. It is fast enough to cross the United States in minutes. It is fast enough that, if you used a simple straight-line intuition, you would reach the moon in under a day. It was fast enough to get to Pluto in under a decade, which is why New Horizons became such a landmark mission. So that sounds like the kind of speed that should finally start to matter. But against a 4.25 light-year target, it is still glacial. That is the part that needs to land hard. Spacecraft speeds that feel extreme inside the solar system still collapse when you compare them to the nearest star. A mission can be fast enough to leave Earth harder than anything before it, fast enough to cross planetary distances on a timescale people can emotionally understand, and still be nowhere near fast enough for interstellar travel to become practical. The solar system is large enough to reward that kind of speed. The gap between stars is large enough to make it feel small. Then comes the curveball. Because maybe you say, fine, Voyager is old and New Horizons is fast at launch, but surely our actual top speed record must start changing the picture. That is where Parker Solar Probe changes the tone. Parker Solar Probe has matched a record speed of about 687,000 kilometers per hour, or 430,000 miles per hour near the Sun. That is the fastest a human-made object has ever moved. NASA has compared that kind of speed to crossing from Philadelphia to Washington in 1 second, or from New York to Tokyo in less than a minute. Those comparisons sound almost absurd because by ordinary standards they are absurd. Parker is moving at a rate that makes most human ideas of speed useless, and even that is still not enough to make the nearest star a short trip. That is the part where the story stops sounding optimistic. Because Parker is not just fast. It is unbelievably fast by every standard people normally use. And yet when you compare that speed to Proxima Centauri, you still do not get a mission that fits inside a normal human timescale. You get a trip that is shorter than Voyager or New Horizons would manage, yes, but still vastly too long to feel anything like ordinary exploration. So the problem is no longer whether we have built fast spacecraft. We have. The problem is that the whole speed range of current spaceflight is too low for the interstellar problem, and that is where the tone has to harden, because this is the point where a lot of casual space optimism falls apart. Current human spaceflight is not almost there. It is not basically one breakthrough away, in any casual sense. It is not sitting just outside the doorway of the stars waiting for one more engine upgrade. What we have built are machines that are miraculous by solar system standards. That part is true. Voyager 1 is historic. New Horizons was incredibly fast. Parker Solar Probe has reached speeds that sound almost unreal. None of that is being minimized, but the nearest star is the scale that exposes the limit. It shows that our current velocity regime is still very small compared with what interstellar travel actually demands. This is the hard shift in perspective the video needs. Inside the solar system, these machines are heroes. Between stars, they are slow, and that is not an insult to the engineering. It is the measure of the distance. The engineering is extraordinary. The gap is just worse. What feels fast near Earth becomes slow near Jupiter. What feels fast near Jupiter becomes slow near Pluto. What feels fast in the outer solar system becomes heartbreakingly slow when the destination is another star. That is the ladder of the problem. Every time the scale expands, the meaning of speed changes. So by this point, you should stop asking which spacecraft is the fastest, and start asking the more dangerous question, how long would these machines actually take? Because once you do that raw math, the dream does not just get harder, it gets shredded. This is the point where the question stops sounding exciting and starts sounding brutal. Once you stop talking in general terms and do the actual travel time math, the whole fantasy gets cut down very fast. Take Voyager 1 first. If you aimed a spacecraft at Proxima Centauri and somehow gave it a Voyager 1 class speed for the whole trip, the travel time would be about 74,948 years. That is the answer with today's kind of deep space speed. Not decades, not centuries, about 75,000 years. That number needs to be treated seriously because it changes the meaning of the question. Recorded human history is only a few thousand years long. Agriculture, cities, empires, writing, all of that fits inside a span far shorter than this trip. So when people say with current technology, what they are really saying is something much harsher, not for civilization as we know it, not for a mission that remains connected to the same society that launched it, not for a project you can describe in ordinary economic or human terms. A 75,000-year trip is not just long. It is so long that the civilization at arrival would have no meaningful continuity with the civilization at launch. And then it gets worse, because the next benchmark is more misleading than most people expect. At New Horizons launch speed, the trip to Proxima Centauri comes out to about 78,359 years. That is actually slower than the Voyager comparison, and that is a very useful shock because it destroys another common misunderstanding. Fastest launch does not automatically mean best interstellar cruise speed. Those are different things. A launch number measures one part of a mission. An interstellar transit needs sustained outward speed in the right frame over the full journey. That is one of the cruel parts of spaceflight. The definitions matter, and space is ruthless about definitions. A record that sounds like the obvious winner can still lose once you ask the real question the right way. So even New Horizons, one of the fastest launches ever, still leaves you with a travel time so long that it barely changes the basic conclusion. The nearest star is still effectively unreachable with that class of technology. Then comes the strongest headline number we have from real hardware. Parker Solar Probe has reached a record speed of about 687,000 kilometers per hour, or about 430,000 miles per hour near the Sun. That is the fastest speed ever recorded by a human-made object. So if anything from current engineering sounds like it should help, it is this. But even here, the math still refuses to cooperate. If you could somehow take Parker's top speed and point it straight at Proxima Centauri, which you cannot do with Parker's actual mission design, the trip would still take about 6,677 years. That is the best current speed headline, and it still loses badly. A 6,677-year trip is not a human mission. It is not a normal scientific program. It is not even most of written civilization. It does not fit inside the lifespan of nations, languages, or institutions in any stable way. So the fastest human-made speed ever achieved does not turn the nearest star into a reachable destination in the practical sense. It only moves the answer from completely impossible on human timescales to still absurdly too long. That is the real emotional structure of the math. The numbers improve, but not enough to change the category of the problem. Then it helps to add a few cleaner speed tiers, because this is where people often fool themselves. They think the issue is that we just need something faster than our current probes, but the problem is much larger than that. At 100 kilometers per second, which already sounds extreme by normal aerospace standards, you are still looking at about 12,741 years to reach Proxima Centauri. At 1,000 kilometers per second, which sounds even more extreme and is far beyond normal current mission speeds, you are still around 1,274 years. That is the point people need to feel clearly. Even speeds that sound outrageous in ordinary engineering terms are still nowhere near enough for a practical star mission. 1,000 kilometers per second sounds like the kind of speed that should break the problem open. It does not. It still leaves you with a trip longer than the lifespan of most civilizations, so interstellar travel does not just need faster, it needs speeds from a radically different order of magnitude. That is the threshold where the whole story changes. At 1% of light speed, The travel time to Proxima Centauri drops to about 425 years. That is still very long, but now at least you are in a regime where the answer starts sounding like a mission for a species, not just a geological process. At 10% of light speed, the trip becomes about 42.5 years. Now the timescale enters the span of a human career. At 20% of light speed, you're at about 21.25 years. Now you're finally in a regime where an uncrewed probe could launch, arrive, and return data on a timescale that humans could emotionally treat as one mission generation. And that is why every serious interstellar conversation eventually ends up in the same place. It becomes a conversation about near relativistic propulsion. Not because that sounds dramatic, but because the timeline refuses to shrink enough any other way. That is the real verdict from the raw math. Current spacecraft speeds give you thousands to tens of thousands of years. Extremely high but still non-relativistic speeds can still leave you with centuries or longer. Only when you start talking about a noticeable fraction of light speed do the travel times compress enough to matter in a practical sense. So the dream gets shredded here for a very simple reason. The numbers do not care what feels fast to us. They only care about the size of the gap. And the gap is so ascendant that almost everything in our current speed range still belongs to the same answer. Too slow. And once you understand that, the next part becomes even more unsettling. Because even the solar system itself is already bigger than most people can mentally handle. People keep underestimating this because they think the solar system ends where the interesting planets stop. It does not. Voyager 1 entered interstellar space at about 122 astronomical units from the Sun, and that milestone was so big it changed the meaning of the mission. It was no longer just a planetary probe, it became humanity's first machine operating in the local interstellar medium. That sounds like the edge of the solar system, but it is not the full edge in the broader sense. The inner edge of the Oort cloud is thought to begin somewhere around 2,000 to 5,000 astronomical units from the Sun. Its outer edge may lie somewhere between 10,000 and 100,000 astronomical units. So even after a spacecraft leaves the heliosphere, even after it enters interstellar space in that technical sense, it can still be deep inside the Sun's long gravitational sphere of influence. That is the first reason that people keep getting this wrong. They think they are done with the solar system much earlier than they really are. And that makes Voyager 1 feel very different once you look at the timeline. NASA says Voyager 1 will not reach the inner Oort cloud for about 300 years. Not 3 years, not 30 years, about 3 centuries. And it might not pass beyond the outer edge for about 30,000 years. That means one of the greatest robotic missions ever built, one of the most successful machines in human history, still needs centuries just to enter the outermost comet reservoir of our own star. And then it needs tens of millennia to get past it. That is the trap. Voyager 1 feels like it has gone unbelievably far, and by human standards it has, but by the scale of the Sun's wider domain, it is still early in the trip. Another star does not even seriously enter the conversation yet. That should reset you immediately. Because if our best deep space probe needs hundreds of years just to get into the Oort cloud and tens of thousands to get out of it, then the nearest star is not simply farther away. It is farther away by a margin so large that even the outer solar system becomes only the beginning of the beginning. Then comes the contrast that really changes the picture. NASA notes that the Oort cloud may stretch 1/4 to halfway from the Sun to the next star. That is an extraordinary statement, because it means the solar system is not a tidy, finished structure ending somewhere near Neptune or Pluto. In the broadest gravitational sense, it is a gigantic fading territory that already extends deep into the gap between stars. That means the space between stars begins before you are done with the architecture of your own star. And that is a much harder thing to hold in your head than the usual textbook picture of the solar system. People like maps with clean edges. They like a bright center, a few planets, and then empty blackness. The real layout is much messier and much larger. The Sun's extended environment does not stop neatly. It thins out across a huge distance, and part of what we casually call interstellar space is still tangled with the long outer structure of our own system. That is why the phrase interstellar space can be misleading. The public hears that phrase and thinks it means the stars are now close, or at least meaningfully closer, but NASA's own numbers force a much harsher reading. Interstellar space starts long before interstellar travel becomes practical. That distinction matters a lot. You can cross the heliopause and enter the interstellar medium, but that does not mean you are close to another sun. It means you have crossed one boundary in the environment around our star. The destination is still vastly farther away. So the phrase sounds like arrival, but in practice it marks only an early threshold. It is a technical milestone, not a solution to the travel problem. And once that sinks in, the rest of the video starts making more sense. Because every propulsion idea that comes later can sound excessive if you still think the solar system is small. If they think getting to another star is mostly a matter of pushing a little harder than Voyager did, then nuclear propulsion, beamed sails, and near-relativistic travel all sound like overkill. But once you understand that even the outer solar system is centuries wide at current probe speeds, those later ideas stop sounding excessive. They start sounding like minimum requirements. You're not trying to make the mission elegant. You're not trying to make it futuristic just for the sake of it. You're trying to make the travel time short enough that the mission still belongs to the same species in any meaningful historical sense. That is the real shift this section needs to create. The obstacle is not just the distance to the nearest star. The obstacle is that our own solar system is already enormous enough to trap slow missions for centuries and millennia before they even clear the outer structure of home. And if that is the scale of the starting point, then ordinary rockets were never going to win this fight. Because once you try to push those speeds higher with normal rockets, the numbers turn savage. This is where normal rocket thinking starts to fail. Up to this point, you can still tell yourself the problem is just distance. Just build a bigger rocket. Just use more fuel. Just launch harder. But this is where that idea breaks. A rocket carries its own reaction mass with it. That means the propellant is not just fuel in the ordinary sense. It is also the mass the rocket throws backward to move forward. And that creates the core problem. If you want to go faster, you need more propellant. But when you add more propellant, the vehicle gets heavier. And then you need even more propellant to push that extra propellant. Then that added propellant also has mass, so now you need even more again. That loop is the trap behind the rocket equation. This is why you cannot just scale up chemical rockets forever and expect them to become starships. At some point, you're no longer building a smarter vehicle. You're building a mass nightmare. More of the vehicle becomes propellant, which forces even more propellant, which eats into payload, structure, shielding, power systems, and everything else the mission needs. The rocket starts spending more and more of its design just trying to move itself. That is the part people often miss. A star mission is not just a long version of a Mars mission. The numbers do not stretch smoothly. They turn against you. And the best way to see that is to look at serious mission studies instead of fantasy numbers. NASA-linked interstellar studies aimed at the outer heliosphere talk about missions reaching 1,000 astronomical units in 50 years, or cruise speeds around 7 to 20 astronomical units per year, using ambitious but still recognizable architectures. Those are not casual concepts. Those are the kinds of mission profiles you get when engineers push known methods hard. Heavy launch systems, gravity assists, careful trajectory design, deep space power, long mission life. This is what today's technology pushed hard actually starts to buy you. It buys you a serious interstellar precursor. It does not buy you Proxima Centauri. That distinction is critical, because 1,000 astronomical units sounds enormous, and it is enormous. A mission like that would be historic. It would move far beyond the current frontier of deep space exploration. It would study the heliosphere from the outside, measure the local interstellar medium directly, and turn a part of space we currently only touch into a real scientific region we can investigate on purpose. That would be a major new era in space science. But then you compare it to Proxima, and the scale gap opens again. The distance to Proxima Centauri is roughly 268,770 astronomical units. So a 1000 AU mission, which sounds legendary on its own terms, is only about 0.37% of the full journey. Not 3%, not even 1%, about 1/3 of 1%. That is one of the most useful numbers in the whole story, because it forces you to separate two very different achievements. A near-term interstellar probe would be a huge success. It would also still leave humanity nowhere near another star. When a serious mission concept reaches what sounds like an almost unbelievable frontier, you are still not even 1% of the way to Proxima. That is the real scale gap chemical rocketry thinking keeps running into. The missions get grander, the distances get larger, the achievement gets historic. And then the nearest star still sits so far beyond that frontier that the category of the problem does not change. Then the energy wall makes it even worse. The nasty part is not only that faster missions need more propellant, it is also that the energy cost rises brutally with speed. Kinetic energy scales with the square of velocity. In plain language, if you multiply your speed by 10, you do not multiply your energy bill by 10, you multiply it by 100. That changes everything. Because the jump from a great solar system probe to a real star probe is not a modest step up. It is not one more generation of better engines in the ordinary sense. It is a move into a new energy regime. A probe that is 10 times faster does not ask for a little more power. It asks for vastly more. A probe that is 100 times faster enters a scale of energy demand that stops sounding like ordinary mission design and starts sounding like industrial civilization directed at one machine. And that is before you add the rest of the mission. Because now the obstacle is no longer distance alone. It is distance plus time, plus propellant mass, plus shielding, plus onboard power, plus communication range, plus reliability over decades or centuries, all compounding at once. The spacecraft must survive longer. It must hit less dust at higher speed. It must carry more capable systems without becoming too heavy. It must communicate over a far greater distance. It must remain functional with little or no chance of repair. Every part of the mission gets harder at the same time. That is the escalation point. This is where interstellar travel stops sounding like more rocket and starts sounding like something much bigger. Not magic, not free physics, not a loophole, but civilization scale engineering. That phrase matters because it gets you out of the wrong mindset. The problem is not that nobody has tried hard enough with rockets. The problem is that conventional rockets obey rules that become punishing when you push them into the interstellar regime. You can absolutely use them for brilliant deep space missions. You can use them to reach the outer planets, the heliopause, maybe even 1,000 astronomical units with enough time and ambition. But when the target is another star, the mass penalty and energy penalty stop being background details. They become the story. And that means every trick inside the solar system starts looking valuable. Gravity assists sundives, every extra bit of speed matters. But even those tricks have limits, and they still do not save you. Gravity assists matter a lot, so this is not the part where you dismiss them. They are one of the main reasons deep space exploration works at all. New Horizons is the cleanest example. It reached Pluto much faster because Jupiter gave it a gravity assist worth about 14,000 kilometers per hour, or 9,000 miles per hour. That cuts it about 3 years off the trip. 3 years is a huge gain in planetary mission design. That is not a minor correction. That can change the entire value of a mission, the timing of the science, and the public life of the project. So gravity assists are not side tricks, and they are not optional details. They are one of the central tools of real deep space engineering. That part needs to be clear first, because otherwise the next point sounds unfair. Gravity assists are powerful. They are just not powerful enough for the problem we are dealing with. A gravity assist does not create free energy from nowhere. What it does is take a small amount of orbital energy and momentum from a moving planet and transfer some of that to the spacecraft. That is incredibly useful inside a planetary system. It lets you reshape the mission path without carrying impossible amounts of extra propellant. It can increase speed, bend trajectories, and make missions practical that would otherwise be too expensive or too slow. But there is a limit built into the trick. A planet cannot casually hand you 10% of light speed. The boost you get is meaningful for solar system missions, but tiny compared with what a practical star mission would need. That is the core issue. Gravity assist can save years. Interstellar travel needs something that can erase centuries or millennia. Those are completely different scales. So then the next idea is obvious. If planets are useful, what about the biggest gravity well in the system? That brings in the Sun. Parker Solar Probe shows what happens when you dive very deep into the Sun's gravity well and use repeated Venus assist to reshape the orbit again and again. Near perihelion, Parker reached about 687,000 kilometers per hour, the fastest speed ever achieved by a human-made object. That is an extraordinary result. It proves the Sun can absolutely function as part of a high-speed trajectory strategy. It is not just a light source at the center of the solar system, it is also a serious gravitational tool, and that is why the Sun starts looking like a possible slingshot machine. In a real sense, it is one. But even here, the numbers refuse to become comfortable. Even that record speed still leaves you thousands of years from Proxima Centauri if you could somehow redirect it outward in the way an interstellar mission would need. So the Sun can help. It can help a lot, but it still does not bridge the gap between fast by solar system standards and fast enough for another star. That is where the solar obverse idea enters the story. NASA-related Interstellar Probe studies explicitly discuss trajectory options like passive Jupiter gravity assist, powered Jupiter flyby, and solar obverse maneuvers. That matters because it shows this is not speculation made up for dramatic effect. These are real trajectory families that professionals study when they want every possible meter per second. When mission designers are trying to push a spacecraft outward as hard as they can, this is exactly the territory they examine. The logic is straightforward. You can use Jupiter to help redirect and accelerate. You can use a deep dive toward the Sun where a burn becomes more effective because of the high speed in the gravity well. You can combine trajectory shaping with propulsion in ways that squeeze much more performance out of the same basic mission architecture. That is smart engineering and it can produce historic missions, but it still does not turn a conventional spacecraft into an interstellar arrow. That is the conclusion that has to land hard here. Planetary assists and sun dives are force multipliers. They can make a good mission much better. They can get you to Pluto faster. They can get you to the heliopause faster. They can get you to 1,000 astronomical units faster. They can open up serious interstellar precursor science far beyond what ordinary mission designs would manage. But they do not solve the fundamental problem. They do not give you the kind of speed that collapses the Proxima timeline into something a civilization can treat as practical. They improve the mission class you already have. They do not change it into a different class altogether. And that distinction matters because it clears the ground for the next honest answer. If the tricks we already know can only take us farther into interstellar precursor territory, then the near-term goal is not reach a star. The near-term goal is something more serious and more realistic. It is to build an interstellar probe. The honest near-term answer is not reach a star, it is build an interstellar probe. That is the most serious version of this idea that exists right now. NASA-associated interstellar probe work is not about sending a spacecraft to Proxima Centauri. It is about reaching the very local interstellar medium on purpose and pushing out to around 1,000 astronomical units. One of the study frameworks describes a mission using today's technology as the first explicit step on the path of interstellar exploration. That wording matters. It is careful and it is honest. It does not pretend we are ready for starflight. It says we can begin building the kind of exploration that points in that direction. That is the grown-up version of the dream. Not a promise that we can reach another sun soon, but a real plan to push beyond the old frontier and treat interstellar space as a place we can study deliberately, instead of just brush against by accident with aging probes. Then look at the actual numbers, because this is where the seriousness of the concept becomes clear. One NASA design reference summary describes an interstellar probe travelling at 20 astronomical units per year for 50 years to reach 1,000 astronomical units. Other related studies talk about around 7 astronomical units per year, again in the context of a mission meant to go much farther and faster than anything we've done before. Those are real mission design numbers. Those are not fantasy speeds in a comment section. By deep space standards, they are aggressive. They would represent a major step beyond the pace of earlier probes. And even then, this is still nowhere near Starflight. That is the point of this section. A mission can be very ambitious, technically credible, historically important, and still belong to a category that is short of another star by an enormous margin. So if you launched in 2026 under this philosophy, the honest line would not be, "We are going to the nearest star." The honest line would be, "We are sending humanity's first purpose-built envoy into the true interstellar environment." That is still extraordinary. That is still the start of something new, and it also carries serious science value on its own terms. You would be measuring plasma in the local interstellar medium. You would study dust beyond the heliosphere in a much deeper way. You would track magnetic fields. You would map the structure of the heliosphere from the outside across distance and time. You would learn how the Sun interacts with the surrounding galaxy. That is not a consolation prize. That is a major scientific frontier. This matters because it resets expectations without killing the ambition. It says the first real step is not arrival at another star. The first real step is building a machine that can survive, operate, and do first-class science deep in interstellar space for decades, far beyond the region where past probes happen to go, then bring back the scale ratio, because this is where the emotional drop hits. Even 1,000 astronomical units only gets you about 0.37% of the way to Proxima Centauri. That is the same brutal fraction from earlier, and it still matters here, because a 1,000 astronomical unit mission sounds like a final frontier when you first hear it. In reality, it is not even 1% of the full trip to the nearest star. So the best realistic near-term interstellar probe is not the opening move of a quick star mission. It is something more basic and more important than that. It is the point where humanity stops standing at the edge and actually starts operating in the ocean. That accomplishment is real, but the destination is still elsewhere. And that is why this section has to feel like both a step down and a challenge at the same time. If we left Earth in 2026 with the most realistic, ambitious architecture, we would not reach Proxima. We would not come close in the usual sense. But we could still do something historic. We could start a new era in which interstellar space itself becomes a laboratory instead of a boundary. That is the better way to frame it. Not failure, but groundwork. Not, we could not get to the star, but we built the first mission designed to live and work in the real interstellar environment. That changes the meaning of progress. It says serious interstellar science begins before star arrival. And once you accept that, the next question becomes much sharper. If normal rockets and clever trajectories only get us to the first serious precursor stage, then where does the conversation finally stop being incremental? It stops there and moves into nuclear propulsion. This is where the conversation stops being incremental. Up to now, you can still stay inside the world of improved rockets, smarter trajectories, gravity assists, and better mission design. That can take you farther. It can make you faster. It can get you to the outer heliosphere or even to a serious interstellar precursor mission. But it does not solve the actual star problem. If you want travel times that stop sounding absurd, you need a propulsion class jump. And mainstream aerospace thinking already knows that. This is not some fringe idea. NASA propulsion assessments and long-range roadmaps explicitly discuss fission, fusion, nuclear pulse propulsion, antimatter catalyzed fusion, and photon sails as candidate paths toward interstellar flight. That matters because it tells you something very important right away. The serious people in this field are not sitting around pretending chemical rockets will eventually get the job done if we just build them a little bigger. They've already admitted the obvious. Conventional rockets alone are not enough. Once you put another star on the whiteboard, the problem changes category. That does not mean nuclear propulsion is magic. It does not mean one reactor solves everything. It means you are entering the hard middle ground, the place between ordinary rockets and the far more extreme ideas like large beamed energy systems. Nuclear propulsion is the point where the dream stops sounding simple and starts sounding expensive, technically hard, and long-term enough to make people uncomfortable. So the next step is to separate the different nuclear ideas instead of treating them all like one thing. The first level is fission and nuclear electric systems. These are powerful because they can transform deep space operations. A spacecraft with a strong nuclear power source does not depend on sunlight the way a solar-powered vehicle does. That changes the mission design immediately. It gives you more electrical power for instruments, more reliable long-duration operations, more flexibility in the outer solar system, and in some concepts, better sustained propulsion through electric thrusters over long periods. That is a real revolution in deep space capability. But that still has to be stated carefully. Better deep space propulsion is not automatically practical starflight. That distinction matters because people hear nuclear and often jump straight to problem solved. It is not solved. Fission can absolutely help you punch farther into the solar system. It can support more ambitious missions. It can improve endurance and in some cases let you build higher performance propulsion systems than chemical rockets alone. But even then, what you're usually getting first is a better deep space ship, not an interstellar ship in the strong sense. You're pushing toward the threshold. You're not casually stepping over it. That is why nuclear changes the conversation without finishing it. It moves you from, we definitely cannot do this with ordinary rockets, into, we now have a serious path toward the regimes that might matter. Then the next escalation is fusion. This is where the speed numbers finally start entering the range that changes the story. One NASA propulsion roadmap summary describes a notional scientific probe capable of cruising at about 0.1 times the speed of light to Alpha Centauri, with a long-range technology path toward a launch around 2069. The word that matters most there is notional. That word does a lot of work. It means this is not operational hardware. It is not a build next decade plan. It is not a solved engineering package waiting for funding. It is a concept in a roadmap, a serious one, but still a concept. That honesty is useful because it lets you say two things at once without cheating. First, no, this is not tomorrow's machine. Second, yes, this is finally the speed regime where an interstellar mission begins to look like a mission instead of a monument. That is the key threshold. At about 0.1 c, or 10% of light speed, the trip time to the Alpha Centauri system falls into the range of a few decades instead of centuries or millennia. That does not make it easy. It does not make it cheap. It does not make it safe. But it changes the timescale enough that humans can start talking about a probe launch, a cruise, an arrival, and the return of data as parts of the same historical project. That is a huge difference. It means the mission could exist inside a civilization's living memory, instead of being handed from culture to culture like a buried obligation. That is why fusion matters so much in this story. Not because it is guaranteed, but because it sits in the first regime where the timeline starts behaving like an actual mission timeline. And this is not a new obsession. That also matters. NASA's archives include studies like Project Longshot and broader interstellar flight roadmaps. So this is not a trend that appeared because people on the internet got excited about exoplanets. Engineers and physicists have been wrestling with this for decades. Generations of serious people have looked at the same wall and tried to find the weak points. They have considered propulsion families, mission architectures, staging ideas, energy sources, shielding strategies, and timelines stretching far beyond ordinary program planning. That tells you something important about the problem. The issue is not lack of imagination. Humanity has imagined plenty. The issue is that the physics invoice stays brutally high no matter which propulsion family you choose. Chemical rockets run into mass limits. Electric propulsion is efficient but often low thrust and slow to build major cruise speed. Fission gives you power and helps a lot, but not automatically enough for practical starflight. Fusion can, in principle, push you into the right speed regime, but now you're dealing with a technology challenge that is already hard on Earth before you even try to make it work inside a spacecraft. Nuclear pulse concepts can offer huge performance, but they come with major engineering issues. Antimatter catalyzed fusion sounds even more extreme and pushes you into a regime where production, storage, and control become severe problems of their own. So the pattern repeats at a higher level. Every candidate path has a reason serious people discuss it, and every candidate path comes with a bill so large that you immediately understand why no one has simply built the thing. That is the emotional turn this section needs. Nuclear propulsion is where the dream becomes serious enough to be uncomfortable. It stops being a cool poster on the wall. It stops being a simple sentence like, "We just need better engines." It starts involving mega-scale infrastructure, reactor systems, pulse concepts, shielding, heat rejection, long-duration reliability, public fear, funding over decades, and a mission horizon longer than most engineering institutions are built to handle. Take shielding alone. A star probe moving at a serious fraction of light speed cannot treat the interstellar medium like harmless emptiness. Dust and particles become impact hazards at those speeds. So now the propulsion conversation is tied directly to materials science and survivability. Take power systems. If the mission lasts decades and travels far from the sun, you need onboard power that remains reliable deep into the cruise. Take heat. Powerful systems generate waste heat, and rejecting heat in space is its own engineering fight. Take program continuity. A project aimed at launch decades from now, and data return decades after that is operating on timescales longer than normal attention spans and often longer than the careers of the people who begin it. That is why this section matters. It removes the last layer of casual thinking. Because once nuclear propulsion enters the frame, you should understand that we are no longer talking about clever upgrades to ordinary spaceflight. We are talking about a civilization deciding to fund, build, and sustain an entirely different level of machine. Not new physics, not fantasy shortcuts, but engineering at a scale and difficulty that most people do not naturally associate with a spacecraft. And that is exactly why it matters. Nuclear propulsion is uncomfortable because it is the first place where the dream starts acting like a real project. A hard one, a dangerous one, maybe a century-long one, but real in a way that ordinary rocket talk is not. And even then, nuclear propulsion is not the only path people take seriously. Because if you want the first concept that makes the nearest star feel like something a single human lifetime could contain, the conversation shifts again. It shifts to laser sails. This is the first idea in the whole story that makes the nearest star start to feel like it belongs inside a human career. Not for people, not for a big spacecraft, but for a machine finally, yes. Breakthrough. Starshot's official concept aims at ultralight nanocraft pushed by a ground-based light beamer to speeds of up to 100 million miles per hour. The stated payoff is a flyby mission to Alpha Centauri in just over 20 years from launch. That is the first real tonal break in this entire subject. Up to now, every serious number has sounded like a sentence handed down by physics. Thousands of years, tens of thousands of years, maybe centuries if you are extremely aggressive. Then laser sails show up, and for the first time the number drops into the span of a human career. That changes the emotional logic immediately. The nearest star stops sounding like a place that only matters to abstract future history and starts sounding like a destination a living generation could launch toward and still hear back from. That is why this concept gets so much attention. Not because it is simple, and not because it is guaranteed, but because it is the first public-facing idea that takes the timeline out of the graveyard range. If the speed target is around 20% of the speed of light, then a 4.25 light-year journey takes about 21.25 years in the Earth frame for the cruise itself. That is the number that changes the room. Once you get into the 0.1c to 0.2c regime, the nearest star stops meaning never in practical conversation and starts meaning maybe for a machine. That is exactly why starshot and related sail concepts dominate serious public discussions of interstellar probes. They are not the only ideas people take seriously, but they are the first ones that make the timeline compress enough for non-specialists to instantly feel the difference. And notice what had to change to make that happen. The trick is not carrying more fuel. The trick is refusing to carry most of the propulsion system at all. That is the conceptual break that matters as much as the speed itself. Starshot is not a crude arc. It is not a conventional probe bus with tanks, engines, and a long cruise under onboard propulsion. The core concept is a nanocraft attached to a light sail, with the push coming from a massive Earth-based laser array. In other words, instead of loading the spacecraft down with the thing that has to accelerate it, you leave the heavy propulsion infrastructure at home and beam the energy across to the sail. That is a complete break from the normal rocket logic that has dominated spaceflight since the beginning. Rockets carry the reaction mass and usually the energy source. A beamed sail tries to outsource the hardest part of the problem to infrastructure that does not have to ride along with the probe. That is why this feels so different from every section before it. The earlier parts of the video were mostly about how current spaceflight loses. This is the first concept that wins on paper by changing the rules of the game. It does not solve the star problem by making the spacecraft a little better. It solves it by making the spacecraft tiny and moving much of the propulsion burden off the spacecraft entirely. That is a very important point, because otherwise people hear laser sail and think it is just another type of engine. It is not. It is a different architecture for the mission, and that architecture comes with a price that is just as dramatic as the speed gain. The official Starshot material openly says hard engineering challenges remain before any such mission becomes reality. That honesty is one of the strongest things about the concept, because it keeps the idea serious instead of turning it into marketing. The challenge is not just building a fast little probe, the challenge is building the whole system that makes such a probe possible. That means extreme beam control across huge distances, sail materials that can survive intense illumination, tiny payloads that still manage navigation and science, communications from another star system with almost no power budget, and guidance precise enough that a very small craft travelling at a huge fraction of light speed still hits the target region. Those are not side details, those are the mission. Because laser sails are the first credible route to multi-decade interstellar probe travel times, but they are still very much a frontier of unresolved engineering. The sail has to be absurdly light and still survive. The beam has to be incredibly powerful and incredibly precise. The probe has to stay tiny because mass destroys the concept, but it also has to do useful science, navigate and communicate. Then there is survivability at high speed. Then there is pointing. Then there is the problem of actually returning information across light years with a payload measured in grams. So yes, the wall cracks here, but it does not disappear. That is why the right tone here is not problem solved. The right tone is, for the first time, the numbers move into the right category. That is a huge difference. You do not need to oversell it. You do not need to pretend the technology is close to deployment. The speed regime itself is enough to change the meaning of the discussion. At current spacecraft speeds, the nearest star is a distance that belongs to civilizations, not missions. At around 0.2 c, the nearest star becomes a mission-class target for a tiny flyby machine. That is the breakthrough in emotional geometry. Before this, every practical sentence about starflight ended in defeat. Here, for the first time, it ends in a conditional maybe. And that conditional maybe matters more than it sounds. Because once you know there is at least one known architecture that can put the travel time into a few decades, even as a concept, the whole rest of the subject changes. The question is no longer whether the universe absolutely forbids us from reaching another star in a useful time frame. The question becomes whether we can build the infrastructure, materials, control systems, and miniaturized spacecraft needed to make that concept real. That is still a huge challenge, but it is a different kind of challenge from the math says no. This is also the first place where the destination starts acting like an actual destination instead of a graveyard for timelines. Again, not for humans, not for a large science spacecraft, not for a mission that breaks into orbit and begins years of remote surveying, but for tiny machines on a flyby? Suddenly the answer is not automatic failure. Suddenly you can say Alpha Centauri in just over 20 years and not be speaking nonsense. That is an enormous shift, and it should feel enormous. But the moment you let that excitement rise, the next problem gets stranger. Because once speeds reach a serious fraction of light speed, another layer of the story appears. People start saying relativity fixes it. And that sounds smart until you look closely. Relativity does not save you until you are already absurdly fast. A lot of people hear the word relativity and jump to the wrong conclusion. They think relativity is the part that makes interstellar travel easy. It does not. Relativity does not give you speed. It does not push your ship. It does not solve propulsion. It only changes how time behaves after you are already moving at a huge fraction of the speed of light. That is the mistake people make. They treat relativity like a shortcut, when really it is the strange consequence you get only after solving the much harder problem first. That distinction matters because it keeps this whole section honest. The theory is not your engine. The theory is what happens after you somehow build an engine, or a beamed propulsion system, or some other architecture powerful enough to push a spacecraft into a truly extreme speed regime. So yes, relativity matters. Yes, it changes the story, but it only starts paying off after the part that is already brutally difficult. That is why you should not think of relativity as a rescue. You should think of it as a weird bonus that shows up very late, after the engineering bill has already exploded. Start at 0.2 times the speed of light, because that is a useful number now. It is roughly the speed regime that makes laser sail ideas like Starshot feel emotionally different from every earlier concept. At 0.2 c, the Earth frame travel time to Proxima Centauri is about 21.25 years. That already sounds completely different from 6,000 years, or 75,000 years, or anything in the current spacecraft range. So the timeline has changed in a huge way, but what about relativity? At 0.2 c, the spacecraft's own elapsed time would be about 20.82 years for the cruise. That is a real relativistic effect. Time on the ship passes a little more slowly relative to the Earth frame, but the effect is modest. It is not the dramatic thing most people picture when they hear the word relativity. You do not get some giant science fiction jump where decades outside become months inside. At 20% of light speed, the difference is there, but it is small enough that it does not dominate the mission. If your architecture is a Starshot-like probe, relativity is not yet the star of the story. Propulsion is still the main event. The reason the mission becomes interesting is not because time dilation saves you. It is because the speed itself is finally high enough to cut the travel time into decades. That is an important correction, because it stops people from mentally cheating. They hear near light speed, and they start smuggling in the really dramatic relativistic effects before they have earned them. But 0.2 c is a good example of the truth. You've already done something unbelievably hard just to get there, and the relativistic payoff is still pretty limited. You get a shorter onboard time, yes, but not by much. The mission still looks like a 20-year class mission from almost every normal human angle. Then push it much harder and the mood changes. At 0.8 c, the Earth frame cruise time to Proxima Centauri is about 5.31 years. That is already remarkable, but now the ship's own experience time drops to about 3.19 years. Now relativity is no longer a side note. Now it starts to bite hard. The difference between Earth time and ship time is no longer something you mention politely at the edge of the conversation. It becomes part of the emotional structure of the mission, because now the spacecraft and the people back home are not even living through roughly the same interval anymore. In the Earth frame, more than 5 years pass during cruise. On the ship, a little over 3 years pass. That is where the weirdness becomes real. That is where interstellar travel stops being only a distance problem and starts becoming a time separation problem too. The travellers and the people they left behind are no longer sharing the same experience of the mission in any intuitive way. Even if the target is physically nearby interstellar standards, the journey is beginning to split time itself into two different human stories. And that is the key emotional turn at 0.8 C. The destination is getting closer in one sense, but the mission is also getting stranger. A lot of people think higher speed simply means a shorter trip, end of story. But once relativity becomes strong, the shortening is not the same for everybody. Earth sees one mission duration. The ship lives another. That is the point where you should start to feel that relativistic travel is not just faster travel. It is travel with a built-in split in reality between frames. Then go to the extreme case, because this is where the idea becomes narratively explosive. At 0.99 C, the Earth frame cruise time to Proxima is about 4.29 years. That makes sense because you are now moving so close to the speed of light that the trip cannot get much shorter in Earth's frame than the light travel time itself. But on the ship, if you ignore acceleration and braking and just look at the cruise, the elapsed time drops to about 0.61 years. That is only a little over 7 months. Now relativity feels shocking in the way people expect. To the travellers, the nearest star starts looking close. Not close in the ordinary Earth sense, but close enough that the trip fits inside less than a year of onboard life. To everyone on Earth, it is still a mission measured in years. That is the point where the same journey stops being one shared timeline and becomes two radically different lived realities. And this is why relativity has such a grip on the imagination, because at those speeds, the nearest star really does stop looking impossibly distant to the people on the ship. The destination compresses, the elapsed time shrinks, the whole meaning of far away changes depending on which frame you're talking about. From the ship's point of view, the trip becomes startlingly compact. From Earth's point of view, it is still long enough that no one mistakes it for casual travel. Both are true at once, and that is where the subject becomes genuinely strange. But this is exactly where you have to undercut the fantasy with the real problem. All of these relativistic gifts only arrive after you solve the propulsion problem for near light speed travel. And that is the hard wall. Not the math of time dilation, the engineering needed to get there. Because getting to 0.99 C is not just a bigger version of getting to 0.2 C, it is a much more violent demand. The energy required is enormous. The shielding problem becomes terrifying. Dust grains and particles in interstellar space are no longer minor hazards. At those speeds, even tiny impacts matter. Navigation becomes harder. Heat management becomes harder. Acceleration itself becomes a major mission issue. Braking becomes another giant unsolved part of the architectures unless you are doing a flyby. And every one of those problems arrives before you get to enjoy the dramatic relativistic payoff. That is the structure people need to understand. Relativity does shatter intuition, but only after engineering has already shattered your civilization's energy assumptions first. That is why you should treat this section like a controlled detonation. At 0.8 C, ship time and Earth time are already separating strongly. At 0.99 C, they become radically different. That is fascinating, and it absolutely changes the meaning of the journey. But it does not change the order of the challenge. First you need the machine, first you need the propulsion. First you need the shielding, first you need the energy. Only then do you get the relativistic effect. And that is a very important discipline in this story, because otherwise relativity turns into a way for you to emotionally escape the real cost. It is not an escape, it is a consequence. The closer you get to light speed, the stranger time becomes. But the closer you get to light speed, the more brutal the engineering becomes too. Those two things rise together. So when people casually say, well, relativity helps, the right answer is yes, but only after you have built something so extreme that current spaceflight barely even counts as the same category anymore. That is why relativity belongs in the story, but not as a comforting ending. It belongs as a reminder of how high the bar really is. The universe will give you the time dilation effect, but only after you pay an almost absurd entry fee. And that means the next twist hits even harder. Because after all the trouble of getting there, after all the speed, all the energy, all the delay and shielding and navigation, the nearest star may still be the wrong star. The next twist is that even if you solve the distance problem, the target itself may still be a bad bet. Proxima Centauri is the nearest star, but NASA's reporting makes one thing very clear. This star is active, unstable, and hostile in ways that matter. It produces powerful flares, and one event observed in 2019 briefly made Proxima about 14,000 times brighter than normal in ultraviolet light. That is not a small burst of bad weather. That is a serious warning about the environment around the nearest potentially habitable system. When people hear nearest Earth mass world, they often picture a useful destination. But the star at the centre of that system is already telling you this is not a calm place. That immediately matters for Proxima B. This planet has a mass of about 1.055 Earths, orbits at about 0.04848 astronomical units from its star, and completes a year in about 11.2 days. Those numbers are exactly why it gets so much attention. It is nearby, roughly Earth mass, and sits in the zone where liquid water is at least discussed in principle. But those same numbers are also the problem. Because Proxima is a dim red dwarf, the habitable zone sits very close to the star. So Proxima B is attractive for one reason and dangerous for the same reason. It lives deep inside the flare and particle environment of an active red dwarf. Then the harsher NASA numbers make the whole target feel less comfortable. NASA's habitability modelling for Proxima B suggests the planet may be exposed to superflares roughly every 2 hours, with estimates that atmospheric oxygen could escape in about 10 million years under those conditions. Separate NASA reporting says worlds in Proxima's habitable zone may receive average X-ray doses about 500 times higher than Earth's, and as much as 50,000 times Earth's during a major flare. That is not a small habitability penalty. That takes the phrase possibly habitable and pushes it towards something much harsher, maybe heavily irradiated, maybe atmosphere stripped, maybe sterilized. And that is where Alpha Centauri A and B become the uncomfortable alternative. NASA's Alpha Centauri reporting suggests the two brightest stars in the system are gentler in current X-ray bombardment terms than Proxima. In fact, the X-ray conditions around Alpha Centauri A are reported as better than around the Sun, while Alpha Centauri B is only somewhat worse. So now the trade-off becomes difficult. Proxima is the closest star and the one with the clearest confirmed Earth mass-style planet. But Alpha Centauri A and B may be the more benign stellar environments, even though they are slightly farther away, and confirmed planets around them are much harder to pin down. That is the real shock in this section. The problem is not just how long the trip is. The problem is that after all that time, the first system you can plausibly target might still turn out to be a terrible place to slow down, settle, or trust as a life-bearing world. The nearest star does not only test propulsion, it tests your assumptions about what kind of system is actually worth reaching first. Closest and best are drifting apart again, and now they are drifting apart in the most painful way possible. That should change how you hear the rest of the video, because once the target itself starts rebelling, interstellar travel stops being a simple race to a point in space. It becomes a much harder question about destination quality, environmental violence, and whether the first star we can realistically aim at is even a place we would want to trust. And if that is the target problem, then the journey gets stranger again on the way there. Because interstellar space is not empty, and talking to your probe becomes its own nightmare. People say empty space because it sounds clean and simple. It is neither. Voyager 1's measurements make that very clear. The interstellar medium is not silent emptiness. NASA describes it as the spread out soup of particles and radiation. And Voyager's data show that it has real structure, real turbulence, and real density changes. NASA also says it is full of waves at multiple scales, some driven by the rotation of the galaxy, some shaped by supernova blasts stretching billions of miles, and some tied to solar eruptions that move through the boundary region of the heliosphere. So the medium between stars is not just a blank backdrop where a probe cruises through nothing. It is an active environment with physics of its own. The void is not passive. The void pushes back. That matters more as speed goes up. At slow speeds, space can feel forgiving because there is so little matter in it. But very little matter is not the same as none, and high velocity changes the meaning of every grain and every particle. NASA and JPL have reported direct detections of interstellar dust flowing into our solar system, including results showing that this dust can be larger and heavier than scientists once expected. That is important because the faster your spacecraft moves, the less harmless the medium becomes. A dust grain that would barely matter at ordinary deep space speeds becomes much more serious when the closing speed climbs into the tens of thousands of kilometers per second. The probe does not need to hit a boulder for this to become dangerous. At extreme speeds, small things stop being small in mission terms. That is one of the hidden costs of every glamorous propulsion idea. You hear 20% of light speed and think about the travel time collapsing. What they usually do not think about is the medium the craft has to survive while doing it. At those speeds, impact protection is no longer a side concern. It becomes part of the core architecture. The spacecraft has to survive a long path through a medium that is thin but not empty, structured but not predictable in the simple way people imagine, and full of particles that become more dangerous the faster you go. So the interstellar problem is not just how do we accelerate, it is also how do we survive the cruise. Then the story gets personal because the communication problem starts long before you get anywhere near another star. Voyager 1 is the proof. NASA's Deep Space Network has to deal with signals so faint that special antenna arraying is needed to pull them out cleanly. In April 2024, all 6 radio antennas at the Madrid Deep Space Communication Complex were used together in a historic test to receive data from Voyager 1 at the same time. NASA also notes that Voyager 1's signal takes over 22.5 hours one way to travel from the spacecraft to Earth. That is not a star mission. That is a spacecraft a little over 15 billion miles, or 24 billion kilometers, away. And already the communication system is operating at the edge of what ordinary intuition can handle. That is why the communications problem does not begin at Proxima. It has been haunting us for decades already. Voyager is still inside the range where the Deep Space Network can work with it using giant antennas and arraying techniques, and the signal is already so weak that NASA highlights just how extraordinary the tracking sensitivity has to be. So when people talk about sending a probe to the nearest star, they should not picture a simple extension of current mission operations. They should picture a communications challenge that becomes one of the defining parts of the mission long before arrival. Now, push that out to Proxima distance and the cliff becomes obvious. To about 4.25 light years away, the one-way light time is about 4.25 years. That means no live conversation, no real-time troubleshooting, no joystick corrections during a crisis, no meaningful sense in which the probe can call home and get immediate help. If something unexpected happens during approach, Earth will not be there in any operational sense. The spacecraft has to be autonomous enough to survive, navigate, decide and keep functioning with no instant guidance at all. Even success would be lonely on a timescale that humans do not naturally handle well. The mission would not just be distant, it would be delayed by design, because physics builds the delay into every message. That changes how you think about the probe itself. A true interstellar probe cannot be treated like a remote-controlled tool in the way people casually picture spacecraft. It has to be more self-reliant. It has to endure longer command cycles, greater uncertainty, and more onboard decision-making. The farther away it gets, the less control means what people think it means. At Proxima distance, the separation is so extreme that the spacecraft and Earth are not really operating inside one shared moment anymore. They are operating inside a chain of messages with years between request and response. That is not just a communications issue, it is a mission philosophy issue. And then there is the data return problem. Even if the spacecraft survives the trip, even if it takes measurements or images, it still has to send that information back across light years. That is a much harsher demand than simply maintaining a carrier signal. The probe may be tiny if it is sail-based. It may have very limited onboard power. It may not have a giant radio dish. It may be doing a fast flyby, not a leisurely orbital survey. So the communications burden and the science burden start fighting each other. The spacecraft wants to be light and fast, but the mission wants it to be capable, stable, and easy to hear. Those goals do not naturally fit together. There is one hopeful note here, and it matters because it shows this field is not standing still. NASA's Deep Space Optical Communications demonstration proved that laser communications can reliably send and receive data over Mars-comparable distances. NASA and JPL report a 267 megabits per second demonstration from over 19 million miles away, and later record-setting data returns from 307 million miles away. Those are major achievements. They show that optical communication can deliver much higher data rates than traditional deep space radio methods in the right conditions, and that it works far beyond Earth orbit. That is a real step forward. But the key phrase is Mars-comparable distances. That is still solar system scale. It is a huge improvement, but it is not yet the same category as talking across light years. The nearest star would demand the next leap after that leap. It would demand systems that can send meaningful data across a far greater distance, with much stricter pointing, much lower signal margins, and much weaker spacecraft resources at the far end. So even our hopeful technology demo is best understood as groundwork. It proves the direction is right. It does not mean the final problem is solved. Space between stars is not a clean black vacuum where a ship just coasts in silence. It is a real physical medium. It has waves, density structure, particles and dust. It is sparse, but it's not empty. Then on top of that, the farther the probe goes, the less direct control matters and the more communication becomes a slow, fragile exchange stretched over years. That means the mission is being challenged from both directions at once. The medium threatens the spacecraft physically. The distance threatens the mission operationally. And that is why this problem is so much bigger than build a faster ship. A faster ship hits the medium harder. A farther ship talks more slowly. A smaller ship is easier to accelerate but harder to hear. A larger ship may carry more capability but becomes harder to push. Every improvement drags a new weakness behind it. That is the pattern of interstellar engineering. The mission is not fighting one obstacle. It is fighting a stack of obstacles that get worse together. So by this point, the answer to the original question is finally ready to be stated in full. Not in fragments, not as separate speed examples, but as the actual verdict. If you left Earth in 2026, how long would it really take? If you mean we launch in 2026 using something in the broad family of what humanity can actually do now, then the answer is not encouraging. It is thousands to tens of thousands of years. Using a Parker Solar Probe speed benchmark, you are looking at about 6,677 years. Using a Voyager 1 class speed, about 74,948 years. Using a New Horizons class benchmark, about 78,359 years. Those are not mission timelines in any normal sense. With present-day spacecraft logic, the nearest star is not a trip. It is an epoch. Parker's record speed is real, and Voyager 1's current speed and distance are real, but the gap to Proxima is so large that even our best hardware still leaves you with timelines longer than most of recorded civilization by orders of magnitude. If you mean aggressive near-term precursor science, the answer changes, but only a little. A serious interstellar probe concept can aim for around 1,000 astronomical units in 50 years, using mission architectures NASA-associated studies describe as feasible with current technology pushed hard. That would be historic. It would transform our knowledge of the heliosphere, the very local interstellar medium, dust, plasma, magnetic fields, and the sun's interaction with the galaxy. But even 1,000 astronomical units is only about 0.37% of the way to Proxima Centauri. So the honest near-term answer is not we reach the nearest star, it is we begin the age of deliberate interstellar exploration. That is still extraordinary, but it is not the same claim. If you allow much more radical propulsion, then the timeline finally collapses into something that sounds like a mission instead of a monument. At 1% of light speed, the trip to a 4.25 light-year target is about 425 years. At 10% of light speed, about 42.5 years. At 20% of light speed, about 21.25 years. That is why every credible starflight discussion either ends in disappointment or jumps into nuclear, beamed energy or sail-based propulsion. The middle ground barely exists. Once you ask for timelines that still matter to a living civilization, ordinary deep space speeds stop being enough almost immediately. Starshot's own concept frames the appeal clearly. Around 20% of light speed, a flyby to Alpha Centauri in just over 20 years. That is the first regime where the nearest star starts acting like a destination for a machine. Then there is the extra time almost everyone forgets. Arrival is not the same as hearing the results. At 0.2 C, the cruise takes about 21.25 years in Earth's frame. Add the 4.25-year one-way light delay for the first signal back, and the first return data would not reach Earth until roughly 25.5 years after launch, if the probe transmitted immediately on arrival. At 0.1 C, the cruise takes about 42.5 years, so first return data comes back at about 46.75 years. That means even your best serious probe scenarios always take longer than the cruise itself, because the universe makes you pay the light travel delay twice, once to get there, and once to hear about it. And that is for a successful mission with no major pause at the destination. There is no live conversation with another star system. There is only patience. So the real answer is this. If we left Earth in 2026, the nearest star would take millennia with present-day spacecraft, decades only with technologies still far beyond operational reality, and a civilization-scale commitment no matter what. That is the answer after all the numbers, all the comparisons, and all the optimism are forced through physics. The stars are not unreachable because the universe forbids them. They are unreachable on human terms because they demand more speed, more energy, more autonomy, more infrastructure, and more patience than our species has yet learned to organize into one working system. The distance is real. The challenge is real. And crossing it is less about launching a vehicle than about deciding what kind of civilization can build one. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.